Our next speaker is our own Mr. Daniel Jafferis, who will speak about wormhole teleportation in the SYK one.
All right, thanks for the invitation to speak and squeezing me in this morning. I think my talk is a little bit of a slightly different topic than the rest of the conference, but I hope it'll still be okay and fun. So this is based on some papers I wrote with my fellow students Miguel and Eric Wall, and then a recent paper that Miguel and I wrote together. So I'm going to first tell you the general idea. This is more like motivation. So it's going to consist of some of the pictures and about this idea of traversable wormholes and teleportation. And then I'm going to describe some setup of the SYK model, this model of n interacting Majorana fermions with some random interactions. And we'll sort of show how to see how the setup works in detail in that SYK model and try to extract some results out of it. So I'm a string theorist. I do gravity-related things. So we're very excited these days about some connections between entanglement and geometry, or entanglement and how space is put together. And the basic idea is that quantum entanglement between two black holes is geometrically realized by having their interior insides joined. So I have a black hole over here and another over here. If I put them in an entangled state, somehow they're connected by a wormhole being behind the horizons. So maybe just say it again, slightly different way. If I have a pair of black holes, one over here, one over here, there's some physical systems. Each one of them has possible states, microstates. And if the state is factorized, I have some state of this one and some state of that one, they just have nothing to do with each other. They could be two different universes, they don't interact, there's no relation. And so, of course, it's described by a disconnected space, one here and something else over here. But the surprising conjecture, sometimes called the R equals EPR, is that if you take a superposition of states like that, which will have entanglement between the left one and the right one, it has an alternative geometric description where the space-time is physically connected. So it looks like you add a handle to your spatial manifold that joins the interior. So that sounds kind of surprising, because we usually think that, by quantum mechanics, if we take superpositions, we don't change the properties, right? To compute the expectation value of topology, we would get trivial, and then here we say somehow it's non-trivial. So there's something a little surprising about it, and so we wanted to probe this more. Now, in the talk today, I'm not going to have anything to do with black holes like in space. The whole story will be in the context of holographic gravity, where I have some strongly interactive quantum system, and it has a dual description in terms of a dynamical space-time in emergent extra directions. So there's a cartoon, so time goes up. My strongly interacting quantum system is living on the circle, and then the interior, there's nothing there. It's hollow, but it gets filled in a sense, by this emergent space. So I could, have a one-dimensional material like this in a ring. There's nothing in the middle, but if I have the right kind of system on it, its dynamics are described as if it was filled in with some space, but a space which is it has a dynamical gravity, so the curvature of the space can change. Now, the extra dimension here roughly represents something like scale or size of operators or the degree of multipartiteness of entanglement. What I mean is what is it in the one-dimensional quantum system that describes something deep in the interior? It's the simple, let's say living on this boundary is a spin chain. If I have simple operations on the spin chain, single site operations, those live near the boundary. But if I take something like the product of n spins or k spins along the chain, that might describe something deeper in the interior. So that's what I mean by the size of the operator. How many sites do I multiply together? This is a rough correspondence. But in this story, if I take the full quantum gravity theory, living in this interior geometry, which in general might include corrections from string theory and quantum corrections, then it will exactly equal the boundary theory. And the kind of thing I have in mind computing are boundary observables. So I have some correlator of the spins or something of the spin chain, and it's a very strongly interacting one, so it might be hard to do that computation, and I can do equivalent, I can do totally different looking computation in this gravity theory, and it's supposed to be if I do them both exactly, I'll get the same answer. So that's the very basic idea. But again, you can take these first slides mostly as our inspiration for this. I can actually do computations in a different way, not using this, but I think this was sort of a motivation. Okay, now what is an example of what the emergent spacetime can look like? Let's say, so in most of the talk I'm going to have an even simpler example in mind. Here we have a quantum system which is like a spin chain, but in the discussion today, my quantum system must be quantum mechanics. So it will be a one-site thing with no spatial extent. So it's just this line. So this is time, and it's like a quantum dot. Right? So I can have two non-interacting copies of the system where the Hamiltonians, of course, is the sum. One is over here, one is over there. They don't interact. And I'm going to often study them in this thermal field double state. This is a state where if I look only on one system, it looks like the thermal ensemble with inverse temperature beta. But it's a pure state that entangles the left system with the right system. Now, the idea is that if this is the correct kind of strongly interacting quantum system, then it has dual description that looks like a two-dimensional black hole. This is sometimes called the eternal black hole. And it has two causally disconnected asymptotic regions. There's no way to send the signal from the left to the right. It better not be, otherwise this picture is clearly wrong because there's no interaction between them. And so, but as promised, the space is connected. If I had a factorized microstate, the psi left and psi right, I would have drawn something on the left and something totally unrelated on the right because there could be two systems that have nothing to do with each other. So in a way, it's kind of surprising to think that if I study them in this entangled state, I should use this connected picture, even though there's no interaction. But there's not a direct contradiction because, as I said, this is supposed to be a space-time diagram, the type where people draw general relativity, where line of causality are 45 degrees. So all objects like people and aliens go always more in time, and you can't go this way. That would be going faster than light. So there's no way to causally get from here to there. So there's no direct contradiction. But the sort of striking feature of this picture is what's shown here. I could jump in. So we each have some quantum dot. I have one, and it's somehow tangled with another one very far away. And I managed to jump into mine, whatever exactly that is. And this idea or conjecture says that if an alien jumped in on the other side, we could meet in the interior. Well, that sounds like a very strange thing. I can meet somebody from far away just using entanglement. But again, there's no direct contradiction because both me and this thing died together in the singularity here in this red garbage. And so neither of us get out and tell anyone that we could meet, so we don't contradict that you can't use entanglement to send information. Okay. Now, this sounds like a cute story, but a little bit funny because since you have the region inside, you can never get out. How do you ever tell in principle whether the story was true? So what we wanted was to see is there some causal way of probing whether, say, this meeting takes place, because it sounds very distracting. And it turned out that the right idea is to think of using the systems, the system meaning this left and right systems, to use those systems in something like a quantum teleportation, in a quantum teleportation protocol, as the reservoirs of entanglement. So these two systems are highly entangled with each other. And one thing I can do with entanglement, I can't use it to send information itself, but I can use it in a teleportation experiment if I also have some other communication. And the conjecture is that the dual description of using this entanglement in a quantum teleportation experiment is that the information goes through the wormhole, and then if I apply classical communication between this side and this side in the appropriate way that, this thing can get through and I can see him over here, I can see the interior, etc. Okay, so that's what I'm going for. Just to remind you what is quantum teleportation, the idea is usually stated in the following way. I have Alice over here and Bob over here, and they initially share an entangled pair of qubits, A and B, which I mark with this line to mean that they're in a bell pair, maximally entangled pair. And then Alice has some qubit of interest Q that she wants to send to Bob. And so what she does is she makes a projective measurement on the QA system into some bell basis. After the result of the measurement, we project these two onto this state, and you can kind of follow this diagram and see that now this qubit has the same pattern as this Q, although it in general will be rotated by some unitary. And given the answer of which of the four bell pairs comes out here, Alice tells that to Bob, and then he can apply the appropriate unitary to get exactly the pattern of the qubit Q in this B register. So that's the usual story of quantum teleportation. And now we want to do exactly the same thing, except that our A will be this large quantum system, and the B will be the left. This will be the left quantum system, this will be the right one, and they start off in this thermal field double state, which is not maximally entangled, but it has a lot of entanglement. And in the discussion here, the qubit you want to send is some order 1 number of qubits, and then this A-B system will have a much larger number of qubits. So then it's okay that these are not maximally entangled. The total entanglement here is still much more than the number of qubits you want to send. Okay, and then the story of our work with traversable wormholes is the following. So if it is to be possible to send a state from the left and retrieve it on the right, this spacetime will look like a wormhole that you can get through, right? If I took a spatial cross-section here, if I had one extra dimension, which is this circle of rotation, it will be connected, so it will be something like that. This is the left, this is the right, go through this tunnel. If I could get through, I'll have a causal diagram that looks like this, where it's possible for a signal to pass through without crossing the horizon and dying in the singularity. So this is what it would mean to send a signal from one side to the other. And it's an effect of gravity that these kind of traversable spacetimes have to be supported by negative energy. So that's why we don't see them all the time, like in real gravity. And the cool, interesting thing is that here the negative energy is provided by the physical effect of the teleportation protocol. So what is the schematically any teleportation protocol looks like? Over here, Alice makes some projected measurement, pi, and which have outcomes labeled by I, and then Bob applies these unitaries ui, given the answer. So that's the same as a total unitary that looks like this. Sum over the different outcomes of these projectors. And we can also rewrite this in the following way. Whatever this projector is some operator, sorry, I don't know why I wrote it on the right and left here. So whatever this projector is, it's measuring the value of some operator, which we can call O left, which has the value x. This is the projector that O has the value x. And then Bob's unitary over here, this is a special case. It turns out to be the right one in this context. Bob applies some unitary where that is a parameter based on some other operator here, and this label x. So if you do this, then the total effect is some interaction term, kind of hopping term from the left to the right. So this is equivalent to a teleportation measurement. In fact, when these are some simple x and p operator, people call this a kind of example continuous state teleportation. But if O left and O right have discrete spectra, it reduces back to the usual story. And with this kind of interaction, you can compute, and I will not do that today, but what we did is we can compute the effect of this on the quantum fields of this holographic correspondence. This thing here, this O left and O right, will be some simple boundary operator, so it's equal to the value of some field that lives, propagates in this space-time. And then when you act with something like that, it makes the particular state of the quantum fields in the space, which is actually sweet state. And it carries negative energy, and it supports this wormhole. So one way of drawing it is, when I do this operation, I send some pulse in, which carries negative energy, and so when my qubit here, which I threw into the system, it's encoded as a physical object, encounters that negative energy pulse, it has a Shapiro advance, a GR effect, where when I encounter, usually you encounter positive energy and I get pushed deeper in and going faster, but here I encounter negative energy and I manage to get out. So that was the space-time picture. But what I want to do today is to check this in a lot of detail in the SYK model.
Excuse me.
Yeah.
So what does negative energy really mean?
No, it means smaller energy than the vacuum.
So the states, do the states exist in the Hilbert space? Or?
Yeah, sure. I mean, here by energy, I mean the local energy, not the total energy. So, yeah, I'm kind of glossing this because this was mostly motivation, but the thing that needs to be negative is the total integral of a certain component of the stress tensor along this line, not the integral over all space of the total. That's positive. Right. So locally in QFT, of course, you can have negative energy, but it's actually pretty hard to get the total energy along such a. It's hard to get the total energy along this line to be negative. If I didn't have a coupling between the two sides, that would have been possible. But it's not as impossible as if I evaluated the energy. So I want to look at this in this SYK model, the section of the defined model. So what is that thing? And actually a kind of generalization of it that's been discussed previously. So we imagine we have a system of n Majorana fermions. Majorana fermions means that they satisfy the algebra that each side anti-commutes with each other, except for itself, where it squares to 1. Okay, that's the dimensions there. And then the Hamiltonian is supposed to consist of some random q point interactions. So that's the q over 2 body interaction. Like. So the original example is when q is 4, and then I have product of 4 Majoranas, so you can think of it as 2 guys help at the same time. But here I have, I'm going to study q body interaction when q is large, but much smaller than n. So I have some random interaction like that, where these are drawn from a Gaussian ensemble with variance given by a parameter curly j, that's going to be the main parameter that controls the strength of interactions. And the main point here is that I don't have lower point interactions. There is no, especially there is no quadratic term, so you can think of it as like a system where in the single particle system the levels are exactly degenerate, and then I have only some multi-body interactions. And this kind of system in large n limit turns out to be solvable in terms of a kind of bilocal collective field, where I take one of the fermions at some time and the same fermion at a later time, take the product of them, that gives me the bosonic operator, and then I sum over my average, if you like, this quantity over all n of the fermions, and that gives me some bosonic variable labeled by 2 times, and one can reformulate the whole theory in terms of those, which I'll briefly review. And then there's a further simplification, even beyond just rewriting the theory in terms of these G's, where at very low energies, the whole story roughly looks like conformal fermions, where this is if this time t is not too small, so that I really see the microscopic Hamiltonian, but it roughly looks like conformal fermions, where the weight is given by 1 over q this parameter, except that the effective time difference is given by some internal clock variable that we might call f of t, which is dynamical and governed by this so-called Schwarzschild action. So that's a very brief summary of the answer to this system. Okay, so it looks like a bunch of conformal fermions, but they're not conformal in lab time, but in some internal system time, which is dynamical and is governed by this action. Now, I'll review again a little bit how to solve this problem. Now, how am I going to use it here? Well, I want to encode a qubit, and so I'm going to take this to be my system. So I have 2 copies of this thing, and I wanted to perform this teleportation setup. So I need to have a way of encoding a qubit. This was made of Majorana fermions, so I can combine pairs of them in an arbitrary way to make direct fermions. Here they're all different, so it's arbitrary how I pair them up. And then the direct number operator will be either 0 or 1, and I can use that to encode my qubit. Now, the bulk dual of this story, in the sense of the holographic correspondence, is roughly, just based on interpreting this paragraph in a slightly different way, is roughly 2-dimensional gravity, a particular theory of 2D gravity called Jafferis gravity, whose modes look like just the boundary time parameterization with this action. So it's just sort of rewriting that in 2D language, coupled to matter fermions. That's these things that from the boundary point of view look like conformal fermions. From the bulk point of view, they just look like massive fermions. But they have their own interactions, so the whole story is a bit more complicated than this. So that's why I say roughly. Now, I want to use this thing to encode code my qubit. One caveat to keep in mind is that the expectation value of this number operator is 1/2 at all temperatures. It's not that I don't have much filling at low temperature, that's what I usually expect, because there's no chemical potential for occupation under it. All the levels were exactly degenerate. But I can still think about the presence or absence of one of these fermions as a feature which could propagate through the wormhole in this holographic set. Okay, so that's sort of the background. Now, how can we, so we wanted to study this in more detail, and also the paper, the study paper will appear at the same time, which has a little bit of overlap. So a good way to keep track of whether teleportation works is to start with have a reference qubit here. So we start with just single qubits in maximally entangled state. Then I want to inject the qubit of interest Q into my system. I use some kind of swap operation. Then I apply the coupling, which is like the communication channel. And then at a later time, I swap something out and measure it in this register. And I want to see whether the pattern of Q ends up in the register T at the end. That will be a success. Now, the way I swap my qubit in is via this operation. This basically encodes 1 or 0 in Q into no occupancy or yes occupancy of this constructed direct fermion. And then the interaction is going to couple the fundamental Majoranas at the left with the ones on the right. If I actually sum up all of them, I can't really express that as just a measurement on the left and an operation on the right because they're Majorana fermions. But if I only sum half or less, then I can express it in that way. And it turns out that works just as well. So this can be replaced by a coupling where I only go up to n/2, and then I can interpret it as doing a measurement here and only sending classical information is doing something over here. But I think that detail is not too important. So then the question is, does it work? Does this allow me to transfer quantum information from Alice to Bob through the wormhole? So the way to check whether it works is to compute at the end of the story, the reduced density matrix between this reference and the final register. And if the mutual information is maximal to log 2, then it means that the qubit got through. And if it's submaximal, it means there's some chance of 0, it means that there's a total failure. Okay, so this is the mutual information, and so one can just directly compute what the, this is these are just single qubit guys, so it's a 4x4 density matrix, and the different elements of it are given by various correlation functions in this double copied SYK model. A typical example is, given the structure of this swap operation, is that one needs to compute things like that, acting with this fermion on the left at the early time, and then conjugating by the interaction, and then evaluating the fermion on the right, this causal propagator, and so on. So there are various pieces which are similar to that. And it turns out that to get perfect fidelity teleportation, you will need this, for example, to be 1. That's actually the maximum value because these are fermions, so the expectation value is always either 0 or 1. So that's so then we went ahead and computed these correlators. Just something to point out is we had to go beyond this Schwartzian approximation that I briefly mentioned. The idea is that this is sort of studied in this paper, this kind of causal propagator, which is what you would also compute to see if there's signaling through the wormhole. It's a little bit weaker than trying to send a whole qubit. As I said, this is just a piece in our story. But this causal propagator at low temperatures, you could try to compute in the leading 1/n approximation, just in the Schwartzian story. That's really equivalent in the gravity to the gravity computation, in which you take into account just the Shapiro advance, the picture that I showed earlier. In a way, it's like saying that the effect of the interaction is to just give a kick to the boundaries, and that can allow it to get through. So originally, the boundaries were parallel, so you can't get through the wormhole, but if you give one of them a kick in, then I can reach it. But if you actually do that computation here, you find a pole that delta goes to infinity in the response, which is obviously unphysical because this thing has to be bounded by 1. And so to really understand whether this story works, you have to go beyond this approximation. And the basic point is that whenever you discuss the microscopic Majoranas, it always goes beyond the approximation of thinking about a particle just moving in the 2D geometry. So we needed to analyze the model more carefully. Now, which people already have set up. Okay, so this double copied SYK model can be solved at large N. This is how people first drive the Schwartzian thing about single copy, but anyway, not a huge difference. So we have these bilocal fields now labeled A, B, labeled left and right. So you can hit right, right, left, right, and so on. And you integrate in these bilocal fields into the action using Lagrange multipliers. And incidentally, if we are studying the theory in the thermofield double state, we can smoothly glue together these left and right, and so on. Bring bilocal fields smoothly at Euclidean time beta over 4, because I start in the thermofield double state, it sort of says that I identify this guy at a certain time with the guy on the left at the appropriate time by the KMS condition. So I stitch it all together, which kind of makes sense because if I computed like just the expectation on the thermofield double state, it's the same as it's closely related to an expectation on just the thermal state of the single system. And then the main part of the story, which this goes back to the paper of Kitaev and Stanford and Mount Sinai and others, if you integrate out the disorder, then you can express the interaction, the Q-point interaction of the psi's in terms of G, and then you can integrate out the Majoranas, and one gets the following effective action for these bilocal fields G and sigma. So that was the basic simplification, and then it has an overall factor of n, so in the large n limit, you can treat this theory semi-classically. So that was the basic story of how SYK is solvable. And then in the low temperature limit, this guy G has a collective mode which looks only like the Schwartzian, but that approximation is not sufficient for us, so we just take this whole G sigma business. Now we had this interaction that was important to get any communication between the two sides. And if I take my left-right guys and I conjugate it by the interaction, it mixes them together. That's what the interaction does. It gives me some hopping between the guy on the left and the guy on the right, the same guy on the right, instantaneously at the time I acted this interaction. And it was easier for us to work in Euclidean time, and a lot of details that I don't have time to go through, sort of follow the formulas that are introduced by this paper. And since this is just an instantaneous interaction, we only applied V at t equals 0 and shut off again. The whole story just means that we have the same G sigma theory, except that as you cross the time of the interaction with either of the two times on which G depends, it has a jump, because as you cross it, I hop can hop guys from the left to the right. And when I solve the whole thing together in one variable, when I have tau here, it means I'm on the left, and then if I get on the right, I sort of use KMS, or beta minus tau, and so on. So that's the meaning of this kind of function. So this is just one of the examples, but there are like matching conditions like this as any of the times cross the different interactions. And so then one wants to solve this. That's actually, even just to treat this classically is somewhat complicated. It involves this double integral because these are my local fields and so on. But it has a big simplification in the large n limit and the large q limit. Studied by these people. And in the large q limit, the classical equation of motion, which in general looks like this, simplifies further. With star here means convolution, because each of these depend on 2 times. And G0 is just the 2-point function if there was no interaction, just the free Majoranas. So it just gives a sign as I flip. And basically, everything is governed by the Liouville equation. So if you define G in terms of G0 by some field we call sigma like this, then you can show that the sigma, the classic equation here is that sigma satisfies the Liouville equation. And so the whole story reduces to just complicated problem of solving Liouville equation with some complicated non-local boundary conditions, and I won't go through it obviously because I'm also running out of time. We'll do just wrap up. And so we found a solution, and then one can continue back to the red signature and find the various correlation functions. Let me just highlight some of the answers. At low temperatures, we get a expression like this. This is a thing whose absolute value is 1, we have perfect teleportation. And importantly, it no longer has the pole that's softened by this 1 over beta j phase, which is the stringy correction, or the thing that goes beyond this Schwartzian approximation. So we get an answer like that. It turns out with this answer at large Q, the fidelity is small, but there's an easy way to make it better if you use the product of p Majoranas in the initial step instead of just 1, where p is about q over 2, then you can achieve perfect fidelity. And the whole analysis works in an identical way. And then you can also study the thing at high temperatures. There, the Lyapunov exponent, which appears in this exponent here, is 2j instead of the maximum exponent. And you can still get perfect fidelity in the limit of where this p is very large. We have product of many Majoranas together. But it would be interesting to understand what's the very stringy gravity dual, and I don't know what it is. And another point that I want to emphasize before I finish on the next slide, I think, is that there is a different kind of regime at very late times where higher corrections in 1 over n expansion dominate because they also grow exponentially. Though that's like when the collision in the bulk picture is extremely Transplanckian and I destroy the guy in the interior instead of having to pass through the wormhole. And then the time evolution effectively just looks like random unitary. So when I act with the interaction of the thermal field double state, basically rotates it by a phase, but when I acted on the state where I threw this thing in very, very far in the past, it's completely scrambled, and so then this just acts with trivial phase. So then I still get some story related to this phase difference. It leads to a kind of interference effect, but to actually send a particle, as in this discussion, it's a very weak effect at low temperatures. But in the high temperature regime, I can still get order 1 fidelity teleportation, but again, it doesn't really have a nice gravity dual because SYK null at high temperatures looks very stringy. So that was the story. So we found the detailed teleportation protocol using the SYK model that's described by information passing causally through the traversable wormhole, and it involves only simple operations in terms of the basic Majoranas. And you should contrast it with some other things if you want to follow the story, where at very late times there's some interference effect that does result in some transmission of information, but only allows you to transmit particles or quantum information at very high temperatures. And then the gravity dual description isn't null, or maybe there isn't a very nice one. And in the story, we basically use this technology of finding solutions of SYK at large n in this large Q limit. And the interaction into some kind of twist boundary condition, and that was how we found the answer. So thanks.
Maybe one quick question, if any.
Just to make sure I got the essential point. So in the SYK model, you're able to calculate in great detail this teleportation scheme, check that it works. So, leaving aside this high temperature business, so but low temperature, you're able to do the similar calculation on the gravity side and show that it's indeed this traversable wormhole.
Yeah, and in a sense, that was already done. That was in a sense already done, but we wanted to we wanted particularly to do a computation where we checked whether particle gets sent rather than just signals are sent, which is slightly different. And if one wanted to discuss teleportation, you need to send a particle, so the signal is not enough. So that's sort of the main difference, and that also works. But to do that computation, you have to go a little bit beyond just thinking about the gravity approximation. If you imagine that you encoded your qubit in something written simply in terms of the basic Majorana, just because that guy is not so simple in the gravity language. Only if you smear in time a bit, but then it will be a more ugly thing in terms of the basic Majorana. But the message is that this doesn't screw things up.
Just quickly, it's fine. So you consider Majorana SYK. When one change to complex fermi of SYK, how part of the result still maintained? Is there something changed?
Right. That's a good question. We looked at that a little bit, and everything is pretty similar. And in fact, there's an interesting regime where, for some, like if you turn on a little bit the chemical potential, then there's an interesting regime where, as I said at the beginning, it's a little funny to think of encoding a qubit in this number, occupation number, because it's expectation value of 50-50 from the beginning. But if you're in the direct SYK with some chemical potential, then you can start in states where this is small and everything still works. But the analysis is more complicated. We didn't even include it in this. But it's very similar story.
So let's thank the speaker again. No meat packets about that.
Right. So my speaker packet, I just need everything which is suppressed. I don't really know how to describe it.
Oh, yeah. But there is not too much.
Yeah, anything that goes down.
The whole thing is pretty good. Like,
What is
great.
Yeah, that's
I see the axis of
Oh, okay.
really
Yeah,
but I think it's just a this
this thing is
the
gradient is very strong.
So X
Hey,
good
to see you.
Hi.
So this is oh, hey, center.
Hi, nice to meet you.
So he will be the seminar on Thursday.
Yeah, so I'm in Princeton. I'm back and my flight lands at around 11 a.m. so I may not be able to. But I'll see if I can make it to your talk tomorrow afternoon here. Okay. Before I catch my flight. It'll be cutting it a bit close. But
You're spending only one night in Princeton?
yeah, no, my wife is away, so my kids are going to be alone at home.
Oh, tomorrow is Tuesday.
Tomorrow's Tuesday, yeah. So I arranged the date long before my wife decided to come at the same time. Very complicated.
Oh my god.
are you going to be around?
Yeah, but when is it on Thursday?
11.
Nice to meet you.
I feel you.
Oh, okay.
I'm
Yeah,
already
yeah,
there.
yeah. Nice to
We
meet
could
you.
also maybe
I did have
reschedule to different time actually.
Yeah.
It's very flexible.
Yeah, no, as soon as I finished teaching at 2:30, I had to run back home to take my daughter from there. You
What
know,
about
I'm a renormalized single parent for this week.
what about Taiwan? Oh, well, there for you.
Or is it a pure coordinate?
He's here this week, right?
I think it was, so I just remember, the one talking about like not in this one, this was actual geography.
Yeah, this next time, because there's 3 days here, there's 2 hour exam.
Yeah, the mountain.
I have an oral exam this afternoon.
Maybe we
I
can,
have to go to the
certainly
dentist.
we can try to find something.
That makes sense.
Meeting.
Just,
Oh, I mean, I guess we just.
He'll be here also for the workshop.
Yeah, so just show down, you'll hear him talk tomorrow.
no, you hear this one. Oh, I see.
He's speaking at 4:30. 4:30.
No, I won't be.
Yeah, you teach till 4 o'clock. That's right.
I
Yeah.
teach, so tomorrow afternoon I'll be in MIT. I
Yeah.
teach.
Yeah, and some of us have to teach. You know. He's in sabbatical this semester.
Not changing.
Yeah, oral exam. I teach teaching. Ah.
But you're coming up for sabbatical.
I came up last year.
Last year.
I haven't taken.
So Thursday maybe after my class at 4 o'clock.
Oh, there's a colloquium. Ibrahim.
Are you really skipping?
Ah.
So when's the
Ibrahim, Sisse, one of our.
Yeah, we can discuss that.
Yeah, but, you know, this is one of those colloquia that will be recorded. So you can skip the colloquium,
Yeah.
talk to him. That's what I'm going to do because I have to be home.
Yeah.
So I'll just watch the video later.
Yeah.
Yeah.
That'll take my
Oh, so
daughter.
who's also you need to go.
Ibrahim, Sisse.
Oh, I see.
Yeah.
It's not about that. But it seems not too.
I think maybe Thursday. Thursday after 4 o'clock, maybe 4 o'clock,
This
or
one's
4:10, something like that.
Oh, so we, what time is your class?
From 2:30 to 4.
2:30 to 4. Yeah, I think we should keep the seminar at 11 because there's a party lunch at noon.
Yeah.
That many of us will need to go. I think Leonid will be there. Yeah. Well,
My service schedule is totally.
Yeah, well, the oral exam takes up 2 hours. Right? It's,
And then I need to go to the hospital, have a doctor appointment.
oh no,
And then I come back and 2:30.
and teach. Yeah.
teach. Oh God.
Yeah.
I'm also here Friday morning.
Friday.
You'll be in town Friday.
I'm in town on Friday.
Friday is also tricky. Friday
Also,
morning I
follow
have
up
an
when you're first
appointment.
invited.
Physical
Hey,
therapy.
I'm not supposed to meet him one-on-one.
That's fine. That's
So I
fine.
can meet him in public, but not one-on-one. Because I'm on the Papalodo committee.
Oh.
The rules are that we can't
So
have.
Friday